In this video I am going to explain about iBGP peering. If you want to understand the basic concepts behind the iBGP peering is, you first want to know that what do you mean by iBGP. iBGP is the peering between the same autonomous system. If the neighboring router interfaces are in the same AS number, then it is said to be iBGP peering. So there are three different ways we can do iBGP peering. In order to form an iBGP peering, one requirement is there, that is, all the internal routes should be known with the help of IGP, that is Interior Gateway Protocol. So either AGRP or IP or by means of any static routing, all the routes to reach the network of each iBGP peering should be known with the help of IGP. So first step in iBGP peering is you have to use IGP for reachability purpose. So for that purpose I am going to run AGRP in the interfaces of R1 F0 by 0 interface, R4 F0 by interface, R5 F0 by interface. In all the interface internal to the AS number 100, I am going to run AGRP. The autonomous system for AGRP I am going to use as 10. The network that I have used in R1 F0 by interface is 13. All those things are marked as 13/8, 34/8, 35/8, all those are networks. So from R5 there is reachability to 13 network, so we can form iBGP peering within the autonomous system number 10. In three different ways you can perform iBGP peering. The first method is fully meshed iBGP peering. In fully meshed iBGP peering you need to peer with each neighbor. And another thing I want to say that R1 and R2 are the routers which is in different autonomous system, that is F0 by 1 interface is in autonomous system 100 and F0 by 0 interface is in autonomous system 200. From R2 I have advertised 3 networks. The type of eBGP peering between R1 and R2 is direct peering, and R1 is getting the routes. Show IP route. R1 is getting routes from the iBGP peer R2, that is, you can see here 70 network, 60 network and 50 network are advertised by the iBGP peer R2. Now I am going to peer with internal routers. First I am going to pair with R1 with R3. You can see that now R1 is paired with R3. The type of peering is called iBGP peering because both are in the same autonomous system number. Now the routes that is advertised by the external iBGP peer from R2 is received by R1, and this iBGP peer gives the routes to the R3. So you can see the routes show IP BGP. So you can see that the network that is get from the iBGP peer R1, that is 15, 16, but here you can see that the next hop information is not changed by the iBGP peer. So you need some external configuration to change the next hop information so that this network becomes valid. Here you can see that not valid, valid and best. Here you can see that now the network is valid but it is not best. This is the reason behind is this next hop information 12.0.0.2 this information is not reachable via IGP. Also you need to understand that if you want to reach this network, we have to change the next hop information that is advertised by R1. So when R1 advertised, it has to give its interface IP address as the next hop information. In order to do this, some configuration has to be done in R1. So here you have to give neighbor next hop self. This is the basic configuration is required in iBGP peering so that the next hop information is altered by the iBGP peer. So when R2 is advertising a network with the next hop 12.0.0.2, when this route is advertised, for example you can see show IP route. Here you can see that 17. Network is reachable via 12.0.0.2. This is the F0 by 0 interface IP address of R2. So this is the next hop information. So When this route is advertised to the R3 router, it should change the next hop information by giving its interface IP address, that is show IP interface brief. So 13.0.1 is paired with R3, so this information, this IP address has to be given as next hop in the R3. So we have configured to change the next hop information. Here we have changed that whatever the things eBGP peer received from R2 is going to change the next hop information as 13.0.0.1. So from when you come to R3 interface, previously the next hop is 12.0.0.2, now it will change to 13.0.0.1. show IP. Another thing you need to understand that it is not installed in the routing table. 15.0.0.2 is now it will installed because we have changed the next hop information. So from here you can see show iBGP. Here we have changed the next hop information, and also why it has installed means it knows this 13.0.0. information how to reach that 13.0.0.0. so this route 15.0.0. becomes valid and best. Now I am going to configure iBGP peering from R1 to R4. Go to R1, you can see that we have another peer 34.0.0.4. go to R4 interface and check show iBGP summary. 3 prefixes has been received. Show IP BGP. Here also we haven't configured the next hop self information in R1. We haven't changed the next hop information that is advertised by R2. So for each peering we have to mention the next hop self in configuration. So we have to go to R1 BGP 100 neighbor 34.0.4 next hop self. So when you give this configuration, and here you will in R4 previously next hop information is not changed. Now you can see the next hop has been changed and the route becomes valid and best. Here you can see it is valid. How it becomes valid and best? Because the next hop information has been changed and it is known using the routing table. Using IGP, the next hop information is reachable via IGP, so it will install the route in the routing table. Show IP route. So this BGP route is installed in the routing table only when the network becomes valid and best. If the network is valid, it will not place this route network in the routing table. So in order to, another important thing you have to understand, if R1 is pairing with R3 and R3 is pairing with R4, but for example I am going to pair R3 with R5, but I am not going to pair R1 with R5, what will happen? We will see. What happen means, it will not advertise, this R3 router will not advertise the R2 network routes to R5. That is, iBGP route is getting routes from R2, R1, R2. That R1 route is advertised to R3, but this iBGP pair will not advertise to R5. So here you can see that I am going to pair R3 with R5. I am pairing R5 with R3, but I am not pairing R5 with R1. So what problem occur means, it will pair with iBGP pair with R3, but the routes which is get from R1, it will not advertise back to R5. So it is a basic thing in iBGP, that is, it is a loop prevention mechanism. As we know that in BGP the loop prevention is mainly because of AS path attribute. So within the AS there is the autonomous system number is same. So whatever the routes that is get from the edge router, that is iBGP pair, that will advertise to iBGP pair, but that iBGP pair will not advertise to another iBGP pair. For example, R3 is iBGP pair with R5. The route installed in R3, for example, when you go to R3, show IP route. Now you can see the route 17.0.0 is obtained from the R1 13.0.0.1. This is the valid route, it is the installed route, but this iBGP route is not advertised to R5. You can check in R5, show IP BGP. Here there is no route that is advertised by R3. So what iBGP pair, the routes get from the neighboring edge router will not advertise back to its iBGP pair. So what is the thing you have to do means, you have to fully meshed BGP pairing with internal BGP routers. That is, for example, you have to, from R1 you have to pair with 35.0.0.5, that is R5 router, remote AS is 100, and also give the configuration file next of self. Remote is 100 neighbor next of self, and go to R5. You have to pair with the edge router. .0.0.1 remote is 100 neighbor. Okay, here you can see that now R1 is fully meshed pair with R3, R4 and R5. Now you can see the BGP route installing in the routing table. This is valid and best. Show IB route. Previously we haven't received these routes in the routing table of R5. This is because the edge router has to be paired with internal iBGP routers. So fully meshed, this type of configuration is fully meshed iBGP pairing in order to avoid loopholes inside the iBGP pairing. iBGP, the internal autonomous system routers, we should fully mesh the iBGP pairing. If there is n number of routers inside one particular autonomous system, then we have to create n into n minus 1 by 2 number of pairings configurations you have to do. So there are different techniques are there to reduce the number of configuration required for iBGP pairing. One of the thing is creating a peer group. This is the first method that will reduce the number of configuration in iBGP pairing, and the second one is route reflector. In route reflector, it will reduce the number of configuration from n into n minus 1 by 2 to n minus 1. For example, if there is 16 router inside a autonomous system, then it requires you can see that 16 minus 1, that is 15 into 16. So you just need, for example, if you are having n is equal to 6, for example, then it requires 15 number of configurations for fully meshed iBGP pairing. But if you are using route reflectors, that configuration will reduce from n minus 1. That is, if you are using 6 routers inside autonomous system, then it requires only 5 configurations. So this is one of the method of reducing the number of configuration overload in iBGP pairing. And another method called confederation. So this is another method. In this method, each router or cluster of router can be considered as private autonomous system. That is, each cluster will be paired with the private eBGP number, a private eBGP autonomous system number, both. But for the outside world, it will be look as a whole of one public autonomous system number. The next video I'm going to explain about one by one, that is how to perform how to configure BGP peer group, and how to configure route reflector, and how to configure confederation ID.